Hey guys, what's up? My name is Gabriel Alfredo Seguenza, and this is our presentation on linear programming and its applications. That's me in the little corner over there, but I'm going to replace myself with a little cartoon dude, because I'm pretty sure you don't want to stare at my ugly mug. So without further ado, let's get started. First, I'll just go over a brief overview of what you can expect to learn from this slide deck and lecture. We'll start with an introduction and the basics of linear programming presented by yours truly, where I'll briefly go over the components of a linear programming problem, talk about sensitivity analysis and post-optimality, and I'll go over a short example. After that, my fellow professor Artavan will talk about the simplex method and basis exchange. He'll do a quick overview of the simplex method, show how linear programming problems can be represented algebraically, and he'll go over a simple example as well. Then Professor Celine will take it away with some instruction on duality, problems, and the interior point method. Finally, we'll go a little bit more into what some of the applications of linear programming are, as well as a few examples led by Professor Kelly. So we'll start with what is linear programming. Well, linear programming is a mathematical model that focuses on linear relationships and finds the most optimal path or solution. In other words, it's a set of techniques and computational tools used to solve systems of linear equations and inequalities while maximizing or minimizing some linear function. We can use these techniques to solve complex planning problems in which the relationships are represented by linear relationships. It's sometimes referred to as mathematical optimization. Here we have a simple formula which we could probably all recognize from algebra and calculus, ax plus by equals z. And here we have some operating limitations represented by cx plus dy must be less or equal to e, and fx plus gy must be less than or equal to h. More on that in a second. Why is it important? Because linear programming and its applications are useful in lots of fields, including scientific computing, economics, technical sciences, manufacturing, transportation, management, energy, and even the military. The list goes on. Before we dive into our mathtastic voyage, let's talk a little history. Because linear programming dates all the way back to 1827, where the problem of solving a system of linear inequalities was first published by Fourier. Good old Fourier. Linear programming also has a very interesting history in relation to its classification as a military secret. Believe it or not, during World War II, linear programming emerged as a powerful mathematical tool for optimization, enabling efficient resource allocation, logistics planning, and decision-making. Its applications were deemed strategically valuable, especially in military operations. Also, a Soviet mathematician formulated a linear programming problem equivalent to the general problem, along with a method for solving it that we're familiar with today. So, as such, its classification as a secret apparently wasn't known until about 1947, when many post-war industries discovered it was valuable as a technique for economical applications. The classification around linear programming gradually eased as its applications became more widespread in various industries, academia, and non-military sectors, eventually leading to the widespread adoption and development of operations and optimization research. It was proven to be solvable in polynomial time in 1979 by Leonid Khachiyan. And then, by 1984, Narendra Karmarkar introduced interior point method for solving linear programming problems, which my colleague will introduce a little later on in the slides. There are four components of a linear programming problem. The objective function. This is the equation that needs to be maximized or minimized. It's a linear function of the decision variables. The second is decision variables. These are the variables that the problem seeks to determine. They represent the quantities to be determined or optimized. The third is constraints. Constraints are the limitations or restrictions imposed on the decision variables. They're expressed as linear inequalities or equations. And finally, there are non-negative constraints. In most LP problems, variables can't take negative values. These constraints ensure that decision variables are non-negative. When these are all combined, they form a complete linear programming problem, aiming to optimize, whether that's maximizing or minimizing, the objective function within the constraints provided. Solving a linear programming problem involves finding values for the decision variables that satisfy all constraints while optimizing the objective function. Let's go back to our formula from earlier. We know now that z equals ax plus by is considered our objective function. Our operating limitations are considered our constraints. So we imagine that we have a system of linear equations and inequalities. These systems have many possible solutions. Linear programming allows us to find a particular solution to the system that corresponds to a maximum or minimum of some other linear function. In this case, we need to find x and y such that the red-blue inequalities, as well as the inequalities x is greater than or equal to 0 and y is greater than or equal to 0 are satisfied. At the same time, our goal is to find the largest possible value of z, or the smallest possible value of z if we are minimizing. The independent variables we need to find in this case, x and y, are called the decision variables. You can model many different linear relationships this way. Just as an example, we can say like the company has 40 units of wood available. They manufacture chairs and tables. Each chair requires 2 units of wood, 1 unit of labor. Each table requires 4 units of wood and 2 units of labor. And the company has 16 units of labor available. These don't exactly match what I have written here, but let's say that the profit per chair is 30 and the profit per table is 50. So in this case, we have the maximize z equals 30x plus 50y. If you let x be the number of chairs produced and y be the number of tables produced, the objective function to maximize profit would be to maximize z is equal to 30x plus 50y. And then we can put some arbitrary constraints. Non-negativity constraint is just xy is greater than or equal to 0. We can apply this LP problem, and in some cases we can try to find an optimal solution if one exists. So say they have some constraints, they can be anything, represented by these different colors. You might end up with something like this. We plot the optimal point and notice how the blue line creates a shaded area. The shaded regions are violating the conditions, and the vertex of the unshaded region furthest from the origin can give the optimal combination. It's just a simple example, but LPs can be extremely complex. Likewise, some LPs are infeasible. In this case, they produce 0 tables because the labor cost is too high for tables, and they can make it with less labor and less wood, maximizing their profit. Finally, let's talk a little bit about sensitivity analysis and post-optimality. The previous example will help in understanding this a little bit. Sensitivity analysis involves examining how changes in the coefficients of the objective function or the constraints affect the optimal solution. It helps in understanding the robustness of the optimal solution under varying conditions. If the coefficients of the variable in the objective function change, sensitivity analysis determines how much the optimal solution changes. It assesses how sensitive the optimal solution is to changes in these coefficients. There's also something called constraint coefficients, where if fewer or more resource sources become available on the right-hand side of the equation, those changes need to be analyzed as well. Shadow prices are the price that fluctuates when a company is willing to pay less or more for extra product. These prices indicate the rate of change of the objective function per unit increase in the right-hand side of the constraints. They help identify which constraints are more critical in the current solution. Finally, allowable ranges. Allowable ranges identify the range for the coefficients in the objective function and the right-hand side values of the constraints. These ranges indicate how much the coefficients or resources can change without affecting the optimality of the current solution. Graphs, charts, or plots help decision makers interpret and make informed decisions based on LP model's behavior. Here's just an example. If we change the original objective function, we can end up with a modified objective function, plot them side by side. This can lead to further analysis to figure out what the optimal solution is and create a more robust solution, as well as harden our optimal solution against various conditions and changes in the future. All right, well, now that we've explored the critical insights provided by sensitivity analysis, let's delve into the powerful engine that drives these optimizations, the simplex method. While sensitivity analysis reveals how robust our solution is to changes, the simplex method serves as the backbone, systematically navigating through constraints to pinpoint the most optimal solution. Let's dive into the mechanics of this algorithm and witness how it refines our understanding of the problem's landscape. At this point, I'll hand it over to my colleague Ardavan to continue with the presentation.
Hello everyone, my name is Ardavan Sharafat and I'm going to talk about the simplex method and basis exchange. The simplex method is a mathematical algorithm used for solving linear programming problems. Linear programming involves finding the best outcome in a mathematical model whose requirements are represented by linear relationship, like a maximum profit or minimum cost. There are 4 key elements in simplex method. The first one is objective function. So this is what you're trying to maximize or minimize. For example, it could be the profit or cost. Second, it is constraints. These are the limitations or requirements of the problem, expressed in linear equations or inequalities. Third is feasible region, the set of all possible points that satisfies the constraints. The solution to the linear programming problem lies within this range. And the fourth is vertices of the feasible region. So in linear programming, the optimal solution will always be found at a vertex or a corner point of the feasible region. So how the simplex method works? The method begins at the vertex of a feasible region. This could be the origin or another point. And then the method moves from one vertex to another adjacent vertex. At each step, it evaluates whether the move will improve the value of the objective function. The pivot operation is a process of moving from one vertex to the next. It involves choosing which variable to increase and which to decrease. The variable that we are increasing is also called entering variable, and the one that we decrease is called leaving variable. If you are maximizing, you move towards vertices with higher values of the objective function, and if minimizing, you move towards the lower values. The process stops when there is no adjacent vertex that improves the objective function, indicating the optimal solution has been reached. Linear programming problems are convex, which means that the feasible region is a convex set and any local optimum is also a global optimum. This property ensures the effectiveness of the simplex method. The basis is a set of variables that provide the solution to the linear equations. So the method involves exchanging one variable in the basis with another variable in the basis to move to a new vertex. There are 3 considerations when it comes to simplex method. The first is efficiency. So for most practical problems, the simplex method is quite efficient. Though in theory, it can take exponential time in the worst case. The method is typically implemented using a tableau form, which is a tabular representation of the linear program that facilitates the computations. And the simplex method is widely used in various fields such as business, economics, engineering, transportation, and military applications for solving optimization problems. Formulating linear programming problems algebraically involves translating real-world scenarios into a mathematical model composed of an objective function and a set of constraints, all expressed in terms of linear equations or inequalities. So the first step would be to identify the decision variables. Decision variables represent the choices you can control or decide upon the problem. So for example, if you're planning your production levels for two products, your decision variables might be X units of product A and Y units of product B. The second step is to define the objective function. So the objective function is what you're trying to optimize, maximize or minimize. And it's a linear expression in terms of the decision variables. So for example, if each unit of product A yields the $5 profit and each unit of product B yields a $10 profit, your objective function to maximize total profit would be Z equals to 5x plus 10y, where Z represents total profit. The third step is to establish the constraints. So constraints represent the limitations or requirements of your problem. They are usually inequalities, but can also be equalities. If you have limited resources like only 100 hours of labor available and product A requires 2 hours per unit and product B requires 5 hours per unit, a constraint could be 2x plus 5y is going to be less than or equal to 100. The fourth step is to include non-negativity restrictions. So in most linear programming problems, decision variables can't be negative, as they often represent quantities like amounts produced or hours worked. So for each decision variable, add a non-negativity constraint, like x and y greater than or equal to 0. Alright, now let's consider a simple example. Imagine you run a factory producing two types of chairs, a standard and luxury, and your goal is to maximize profit. So in this case, decision variables are going to be S, number of standard chairs produced, and L, number of luxury chairs produced. In the problem, it says that the profit from each standard chair is $50 and profit from each luxury chair is $80. So maximum total profit is going to be P equal to 50S plus 80L. However, there are some constraints, so we can't just produce luxury chairs. The first constraint is the material constraint. So we have only 30 units of material available, and each standard chair uses 1 unit, and each luxury chair uses 2 units. So this becomes an inequality where S plus 2L should be less than or equal to 30. The second constraint is the labor constraint. So we have only 40 hours of labor available, and each standard chair requires 1 hour, and each luxury chair requires 3 hours. So that means that S plus 3L should be less than or equal to 40. The third constraint is the demand constraint. Market research shows you can sell up to 420 standard chairs and 10 luxury chairs. So S should be less than or equal to 20 and L should be less than or equal to 10. And lastly, we're going to have the non-negativity constraint. Since we can't have negative chairs, S and L should be greater than or equal to 0. So the final formulation for maximizing P should be 50S plus 80L, and it is subjected to the following constraints, where S plus 2L should be less than or equal to 30, and S plus 3L should be less than or equal to 40. S is less than or equal to 20, L is less than or equal to 10, and both S and L should be greater than or equal to 0. So this algebraic representation is how you would set up the problem for solution using linear programming techniques like the simplex method. Now let's talk about the simplex tableau, which is a tabular form used in simplex method for solving linear programming problems. It's a systematic way of organizing and updating the information needed at each step of the algorithm. So here's an overview of how the simplex tableau is structured and used. The first part of the structure is the objective function row. So this row contains the coefficients of the objective function. If the goal is to maximize, the tableau typically starts with the objective function in a form where it's set to 0. The second part is the constraint rows. So each constraint of the linear programming problem is transformed into an equation, if necessary by adding a slag, surplus, or artificial variables, and occupies a row in the tableau. The tableau distinguishes between basic variables, those currently solving the equations, and non-basic variables, the ones initially set to 0. The basic variables make up the initial solution. The rightmost column represents the current values of the basic variables, corresponding to a corner point in a feasible region. During each iteration, a pivot element is selected for the basis exchange. It's chosen from the non-basic variables columns and basic variables rows based on a specific criteria. Alright, so now that we understand the structure of the simplex tableau, let's talk about the functioning of the simplex tableau. We start with an initial tableau. If the initial system is not in the required form, additional steps like introducing slags or surplus variables or applying the two-phase method may be necessary. The method involves performing pivot operations to move from one basic feasible solution to another. This is done by selecting a pivot column or entering variable and selecting a pivot row or leaving variable. To select a pivot column, we should typically choose the column with the most negative coefficients in the objective function row in a maximization problem. And for selecting a pivot row, this is done by calculating the ratios of the solution column to pivot column, ignoring negative or 0 entries, and choosing the smallest positive ratio. Once the pivot element is chosen, we use row operations to adjust the tableau such that the new basic variables takes the place of the old one in the basics. Then we repeat the pivoting process. In each iteration, the objective function value should move closer to the optimum. The process stops when there are no more negative coefficients in the objective function row for a maximization problem, or no more positive coefficient in a minimization problem, indicating that the optimal solution has been reached. The final tableau gives the optimal values of the decision variables and the maximum or minimum value of the objective function. Now that we have all the necessary tools, let's solve a linear programming problem using the simplex method. In this example, which is a maximization problem again, we want to maximize z by choosing the right x1 and x2. However, this equation is subject to the following constraints, where x1 plus 2x2 should be less than or equal to 8, and x1 plus x2 should be less than or equal to 6. And also we have the non-negative constraint where x1 and x2 should be greater than or equal to 0. For the first step, we have to add variables, a slag or surplus, to turn all the inequalities into equalities. As you can see, we have added s1 and s2 in the first row and the second row, and we have turned them into equalities. So for the first row, we have x1 plus 2x2 plus s1 equal to 8. And for the second row, we have x1 plus x2 plus s2 equal to 6. And we also have added s1 and s2 in the last inequality, which means even s1 and s2 can't be negative. In the next step, we have to write down the simplex tableau. This is where we have to perform the first pivot operation. The entering variable is x2 because it has the most negative coefficient -4 in the 0. And the leaving variable is s1 because it has the smallest ratio. So that means we have to replace these two variables and update the table, which will give us the following table. Then we have to divide row 1 by 2 and add row 2 multiplied by 4 to row 1. Lastly, we need to subtract row 2 from row 3, which is the last operation in the first pivot operation. However, we still have a negative value in the 0, which means we still have not found the optimal solution. So we need to perform the pivot operation one more time. In this iteration, the entering variable is x1 because it has the most negative coefficient -1 in the 0, and the leaving variable is s2 because it has the smallest ratio. Now we have to do the same updates. That means we have to replace these two variables, multiply row 2 by 2, add row 3 to row 1, and lastly subtract row 3 multiplied by half from row 2. At this point we can see that none of the 0 coefficients are negative, which means the optimum solution has been reached. And the optimal solution for this problem is when z is equal to 20, which is achieved at x1 equal to 4 and x2 equal to 2. In conclusion, the simplex method is a powerful and efficient algorithm for solving linear programming problems. It works by navigating through the vertices of the feasible region defined by linear constraints to find the optimal value of a linear objective function. This method, through a series of pivot operations and basis exchanges, systematically explores potential solutions, ensuring that each step moves closer to the optimum. While its theoretical efficiency can vary, in practical applications, the simplex method has proven to be highly effective and versatile, making it a cornerstone technique in the fields of operations research, economic, and business planning. Its ability to solve complex optimization problems with relative ease and precision highlights its enduring significance in the world of mathematical programming and decision making.
I'll be talking about duality, interior point method, and a comparison of algorithms. So previously you learned about the simplex method, which focuses on finding the optimal solution by exploring various vertex points of the feasible region. These vertices represent just a fraction of the broader framework known as duality. Duality is a fundamental concept in linear programming that establishes a very important relationship between two related optimization problems. So the primal refers to the original linear program, and the dual is another linear program derived from the primal. What is the relationship between primal and dual? Well, they're pretty much inversely related. So each variable in the primal becomes a constraint in the dual. Each constraint in the primal becomes a variable in the dual. The objective direction is inverted. So if your primal is maximizing, then your dual is minimizing. Duality theorems establish the relationship between the optimal solutions of the primal and dual problems. Suppose the primal linear program is maximize C transpose X, and the dual linear program is minimize B transpose Y. The weak duality theorem states that for each feasible solution X of the primal and each feasible solution Y of the dual, C transpose X is less than or equal to B transpose Y. In other words, the objective value in each feasible solution of the dual is an upper bound on the objective value of the primal, and vice versa. This implies that the maximum value of X of C transpose X is less than or equal to the minimum value of Y in B transpose Y. The strong duality theorem states that if one of the two problems, that being one of the two primal or dual has an optimal solution, then so does the other, and the values of these solutions are equal. In other words, the maximum value of x for C transpose x is equal to the minimum value of y in B transpose y. What are the possibilities for primal dual pairs? Well, first we need to know that any linear program falls into exactly one of three cases. It's infeasible, unbounded, or has an optimal solution. Weak duality tells us that if both primal and dual are feasible, then neither can be unbounded. Strong duality rules out possibility of one problem being infeasible while the other has an optimal solution. This can be summarized in the table below. So if the primal is infeasible, then the dual is infeasible and unbounded. If the primal is unbounded, then the dual is infeasible. If the primal is optimal, then the dual is optimal. So now we'll go into some linear programming algorithms. And remember that the concept of duality plays a critical role in the development of linear programming algorithms. These algorithms are broadly classified in two categories. The first being basis exchange algorithms. These algorithms, such as the simplex one that you learned about previously, work by iteratively exchanging the basis to move towards the optimal solution along the edges or vertices of the feasible region. So in the picture on the left, you can see a visualization of a basis exchange algorithm. The algorithm moves along the edges of the feasible region and eventually ends up at the optimal solution. The other type of linear programming algorithms is interior point algorithms. These ones traverse through the interior rather than the boundaries of the feasible region to reach the optimal solution. And you can see a visualization of that on the right, where we start at some point and we move through the interior of the region till we find our optimal solution, which is close to the boundary. So I'll go a little bit more in depth into interior point algorithms since you guys already got a look into basis exchange algorithms. So there are various techniques that fall under the vast umbrella of interior point algorithms. We won't go into all of them in detail, but we can discuss what they have in common. So firstly, as the name suggests, they navigate through the interior rather than the edges or vertices of the feasible region defined by constraints. They employ penalty functions and barrier parameters to guide the search towards the optimal solution within the feasible region. They follow continuous paths towards the optimum, gradually approaching the optimal solution without necessarily visiting extreme points of the feasible region. And they typically exhibit polynomial convergence rates, providing better complexity for certain problems. So I'll just name a few of the various interior point algorithms and give like a short description. The first one I'm going to mention is Hutchian's ellipsoid algorithm. This was the first ever interior point method for linear programming, and it influenced many future algorithms. It really wasn't an efficient solution, but it was groundbreaking, so I thought that I would mention it. It operates geometrically using ellipsoids to enclose the feasible regions. Next is the primal dual interior point methods. These algorithms simultaneously update primal and dual variables to progress towards the optimal solution. Some examples are affine scaling method and the predictor corrector method. Next are barrier methods. Barrier methods involve introducing a barrier or penalty function into the objective function to guide the algorithm to the interior of the feasible region. A really common example of this is the logarithmic barrier method and the exponential penalty method. Last example that we'll discuss is the path following algorithms. Path following algorithms follow a trajectory or path towards the optimum within the feasible region, often by gradually decreasing a parameter that controls the movement towards the optimal solution. Some examples are potential reduction method and the central path method. So we'll go over the pros and cons of the two main types of algorithms. So basis exchange algorithms, some of their pros are that because they're intuitive, they're very easy to implement. They align really well with math, and so it's really easy to implement them. They're also effective for small to medium scale problems. Some cons are that they're limited applicability, so they might not be as efficient or suitable for certain problems that have more complexity to them. They also are not very efficient for larger problems. They may be slow because they rely on traversing vertices and edges. Interior point algorithms. Some benefits to these algorithms are that they're very efficient for large-scale problems because they go along the inside of the feasible region. Another benefit is that they have polynomial convergence, so they find the answer to the problem relatively quickly. Some cons are their complexity, and I don't mean time complexity. I should have been a little more clear here, but I mean complexity for implementing. Just like the basis exchange algorithms are simple and easy to implement, these interior point algorithms are a little bit more complicated. And another con is that they require careful tuning of parameters, such as the barrier parameter, for optimal performance. So they might, in theory, be really efficient, but if you're not good at tuning parameters, then they become less efficient. All right, so what did we learn in this section? Duality is a fundamental concept in linear programming that establishes a very important relationship between two related optimization problems. Each primal linear problem has a corresponding dual problem. Any linear program falls into exactly one of three cases. It's infeasible, unbounded, or has an optimal solution. Also, linear programming algorithms are broadly classified in two categories: basis exchange algorithms, which iteratively exchange the basis to move towards the optimal solution along the edges or vertices of the feasible region, and interior point algorithms, which traverse through the interior rather than the boundaries to reach the optimal solution. These different techniques have their pros and cons, and there's not really a clear winner between the two. So you need to evaluate your use case before choosing one to implement. All right, thank you, and on to the next section.
Hi, my name is Kelly, and I'm going to be going over some applications and examples of linear programming. So in industrial and manufacturing applications, here are some examples of linear programming here. Linear programming can basically help determine the best and most optimal production levels and can consider factors like available resources, production capacities, demand forecasts, and cost constraints. Other examples would be something like finding the best optimal transportation schedule. So basically some examples of where this could be applied would be like inventory management or supply chain optimization. For like supply chain optimization, linear programming can assist by optimizing supply chain logistics, finding like the most cost-effective routes for transportation, while at the same time minimizing shipping costs. It can also determine optimal inventory locations as well. Another example would be scheduling. So it can help create optimal schedules for tasks, machines, or employee working hours to minimize as much like downtime or idle time and increase like utilization. Another example would be allocating resources. So linear programming can help allocate resources such as the workforce, power, raw materials, machinery as efficiently as possible. It can also consider constraints such as an employee's working hours or schedule. You can also consider how much material is available, the maximum machine capacities, and many more. Another example is maximizing profits. So linear programming is used by many companies in this regard to optimize profits as much as possible, while also considering constraints such as production costs, market demand, and resource limitations. It can also minimize waste. It can optimize production processes, which would reduce excess material usage. And if there is any material usage, it can find the best use of that wasted or recycled materials. And then quality control, it can be used in quality control by allowing resources to be allocated to ensure the best quality standards are met while also minimizing costs. So we can show this being used through a scenario. Our example will be a linear programming optimization in a production planning and manufacturing scenario. So we can say we have a company one that produces 3 types of products. We can call them product A, product B, and product C. Due to the current economy, company one is having a tough time and has to limit many of their resources. These resources are things like raw materials, working labor hours, and machinery use time, or how often the machines are running and being operated on. With these constraints, we want to find the best solution for the optimal production quantities of each product, but at the same time, we also want to make sure that the company's profits are maximized as much as possible. So here we can create some variables to visualize everything. So we can say x1 is the number of product A produced, x2 is the number of product B produced, and x3 is the number of product C produced. We can say that the number of raw materials available will be 100 units. We can say that the number of working hours available are going to be 80 hours. And then we can say that the machine running hours available are going to be 90 hours. And then we're also going to include this non-negativity constraint and put it at 0. This just means that we can't take any negative values. For example, you can't really manufacture a negative number of products or use a negative number of resources. So with that information, we can make our equations for our linear programming algorithm. So raw materials is going to be 2x1 plus 3x2 plus 4x3, which is less than or equal to 100 units. This is only because we can only have 100 units of raw materials available as stated above in our constraints. So working hours, we're going to do 3x1 plus 2x2 plus x3, which is less than or equal to 80 hours. Again, it's because we only have 80 hours available. And then machine hours are going to be x1 plus 2x2 plus 3x3, which is less than or equal to 90 hours. The coefficients here are just going to represent the consumption of raw materials required to produce 1 unit of each product. So product A, which is x1, is going to consume 2 units of raw material. Product B is going to consume 3 units, and product C will consume 4 units. And then we'll apply that to the rest of our equations. Again, we have a non-negativity constraint, which we set x1, x2, and x3, which has to be greater than or equal to 0. This equation just shows that we can't have a negative number of products or use a negative number of resources. It always has to be greater than 0. Let me see. And then we have our equation here, which is maximize z, which is going to be equal to 5x1 plus 4x2 plus 6x3. That's going to be our maximal profit equation. These coefficients are going to represent the profit per unit for each product. So these are just hypothetical numbers that I came up with. In like a real world environment, the values would actually be based on like actual costs, revenues, or profit margins associated with producing each of the product. So if we use the simplex method, which we described above, we should get these results. So x1 is going to be equal to 20, x2 is also going to be equal to 20, and x3 is equal to 0, and our maximized z is going to be 180. So this just means that we can say that a maximum profit of 180 units can be obtained by producing 20 units of product A, 20 units of product B, and 0 units of product C. So that's just one example of how we can use linear programming in a manufacturing field. So moving on, we'll be talking about linear programming along with network flow problems. Network flow problems are used to analyze and optimize resource flow. The network is usually represented by nodes and edges. It can also be used to determine the most efficient way to transport things, such as goods, commodities, or information, or anything else, basically from one point to another within a network, while also considering any constraints. Because of this, linear programming algorithms are often applied to network flow problems, as they basically both attempt to optimize profits and efficiency and minimize any constraints. So we can discuss some examples of cases where linear programming algorithms are commonly used in network flow problems. The first one is going to be the shortest path problem algorithm with constraints. This algorithm attempts to find the shortest path while considering any constraints. While linear programming doesn't in itself directly solve this problem, it can still be utilized, especially when the problem calls for some type of constraint. The problem might have some type of constraints such as limited resources or costs with traversing edges. We can make these constraints a linear constraint and use linear programming to minimize the total distance while satisfying those linear constraints. A more common way to solve this actually is using Dijkstra's algorithm. So our next one is going to be the maximum flow problem algorithm. The maximum flow problems algorithm finds the maximum flow rate, while at the same time finding the best and most optimal flow network. It determines the maximum flow rate that can be sent through a networking, while also keeping in mind constraints. So while other algorithms, such as the Ford-Fulkerson algorithm, which is just a max flow min cut problem, or we can also use the Edmonds-Karp algorithm. They're more widely used for this type of problem. Linear programming still contributes to understanding and solving this problem. And then we also have the minimum cost flow problem. The minimum cost flow problems algorithm finds the least expensive way to send flow through a network, and it also considers flow quantities and costs with edges. We can use the network simplex algorithm to solve this. So moving on, we have the transportation and assignment problems. The transportation problem algorithm is basically when goods or commodities are carried from a set of resources to their destinations, while also considering any supplier demand to reduce total transportation costs. This optimizes the distribution of commodities from multiple sources to multiple destinations, while at the same time minimizing transportation costs. And then this quote here, transportation problem is one of the fundamental problems of the network flow problem, which is usually used to minimize the transportation costs for industry numbers of sources and number of destinations, while also satisfy the supply limit and demand requirement. For this one, we can also use the simplex algorithm, as we described earlier, to solve these kind of problems. And we'll give an example of that later on. But we also have the assignment problem algorithm. So it basically assigns tasks or actions that maximizes profits and minimizes costs. This one, we can use the Hungarian algorithm, which is basically just an implementation of the simplex method to solve this. So this is our example of the transportation problem. We can create another example. So we can say we have another company called Company 2. And this Company 2 owns many factories, and they need to ship their goods to many different locations. At the same time, they want to minimize their transport costs as much as possible while also meeting their demands. So they have two factories, which we'll call Factory A and Factory B. They want to ship to two warehouses, which we can just call Warehouse C and Warehouse D. So in this table here, we can see the transportation costs. It costs the company $6 to ship from Factory A to Warehouse C, and $8 to ship from Factory A to Warehouse D. And then it costs Factory B $5 to ship from their factory to Warehouse C, and $7 to ship from Factory B to Warehouse D. So we're just going to assume that these are the transportation costs. So Factory A has 120 units available, and Factory B has 150 units available. Warehouse C needs 100 units and warehouse D needs 120 units. Using the transportation costs, we can come up with our equations here. So which would be minimize Z equals 6x AC plus 8x AD plus 5x BC plus 7x BD. And these are just the routes to where they're going. So like factory A to warehouse C. We have some constraints here in which we can't really ship out more units than what the factories have available. So that's what these equations here show. So these are our constraints, and again, these are the routes of where it's going. If we again perform the simplex method, we're going to get these results, which is x from factory A to warehouse C is going to be 20. From factory A to warehouse D is 100, and then B to C is 80, and B to D is 40. So what this means is that for our most optimal solution in the scenario, factory A needs to send out 20 units to warehouse C and 100 units to warehouse D. And then factory B needs to send out 80 units to warehouse C and 40 units to warehouse D. So this is the most optimal transportation method for company 2, while also minimizing the transportation costs as much as possible. So conclusion, linear programming serves as a versatile tool for optimization. It offers a very structured and mathematical approach to allocate resources as efficiently as possible. It can also solve a lot of really difficult or complex decision-making problems and find the best optimal solutions within defined constraints. There's a lot of applications for it, as we've seen from the examples. From either logistics and manufacturing to finance, transportation, etc. By formulating problems as linear models and leveraging powerful algorithms, linear programming can enhance like certain decision-making processes and improve a lot of outcomes in like real-world scenarios.